So we already watched the short video on the Coriolis effect, this strange effect where things appear to curve when they're moving in a straight line, depending on your reference frame if you're the one rotating. I'd like you to imagine that you're in a car turning a corner, turning left. What's the direction of your acceleration, and what's the direction of the force that acts on you? This is a 2-column question. For 2-column questions, I always do 1 column at a time. So I see the word acceleration. Is the acceleration inwards or outwards if you're moving in a circle? So put a check mark there, put a check mark there, put an X there, put an X there. Then let's move to the next column. Is the net force inwards or outwards if you're moving in a circle? Of course it is, because if your acceleration is inwards, Newton's first says that the net force is also inwards. So check mark X, check mark X. By doing that, now I zoom out and it's easy for me to circle the correct answer. What is the correct answer here? A, B, C, or D? Okay. I learned that trick a long time ago. Otherwise, if I had to keep track of both answers in my head, I've lost track, Sarah, of how many times I've thought the right answer and circled the wrong one because my brain was dumb and couldn't keep track of 2 different things. So, old trick. Explain your answer using relevant principles of physics. Really, this comes out of, if you're accelerating towards the center, that must be the direction of your net force. That's what Newton's first says. If you're accelerating, there's an unbalanced force in that direction. So here's an example of a horizontal circle. We have something called a centrifuge. At the bottom of the test tube, there's a little tiny amoeba. The test tube is rotating with a period. By the way, you might want your purple sheets out. Thank you, Diego, for having yours out. With a period of 9.9 times 10 to negative 4 seconds. Okay. Ooh. Alex, what's example 1 asking me to find? Centripetal force. So no free body diagram. This is straight plug and chug, because you know what centripetal force is? F equals what? So centripetal force, F equals MAC. The real question is, which version of A am I going to use? Am I going to use the one with the V in it, or am I going to use the one with the T in it? Did they give me the speed, or did they give me the period? So I'm not going to use, remember, AC, there's 2 equations. There's V squared over R, and there's 4 pi squared R over T squared. I'm going to use this one. A common mistake, kids go like this. Force equals 4 pi squared R over T squared. This is so complicated, they say that must be the force. That's the acceleration. F equals what? M. I've lost track of how many times kids forget to put the M there. Didn't I find the force? No, you found the acceleration. But now it's plug and chug. The mass is 1.8 times 10 to the negative 9 times 4 pi squared. R is 0.15 all over 9.9 times 10 to the negative 4, don't forget the squared. I would insist all of you type this into your calculator. You need to find if you can do this level of scientific notations and pies and squareds and get the correct answer. So I'm going to insist all of you try typing that in. M 4 pi squared R over T squared. You'll have to find out if your calculator requires you to put brackets in certain places. I know my calculator assumes everything's on the top if I don't put it in brackets. So I didn't put brackets around the top because there's no plus signs. And then I also know my calculator, if I square scientific notation properly, I don't need to put that in brackets. I got 0.018, sorry, 0.01 08755971 ... See if you get that. Okay? Back arrow to see where the error is. It'll put the cursor where the error is. So some things to look at. Did you use a negative instead of a subtract, or a subtract instead of a negative? Otherwise, I'll come look at your calculator if you want. You might need to put a times in front of the pi. You might need to put a times in front of the 4. And this is why I wanted all of you to type it, because different calculators have different operating systems. I know on mine, I have to put the times after the 9. I don't have to put a times between the 4 and the pi. Yeah, I have to put one there. Otherwise, it would think times 10 to the negative 94. Unless you had a bracket there, then maybe, I don't know. Okay? Yeah. Okay, let me pause the video for a second. Don't clear your calculator. Did you all get 0.0109? And that's a force, newtons. Is that a big force? It's massive. It's huge. For this amoeba, it's unbelievably big. I'd like to find out what the acceleration is. Well, if F equals what? How would I get the A by itself? Divide by the? How do you get an A by itself and F equals ma? So on your calculator, divide by the mass of this amoeba, which was 1.8, scientific notation, -9. What's the acceleration that this amoeba is experiencing? Do you get that? How many G's is that? How would I change this to G's? Divide by? This amoeba is experiencing well over 500,000 G's. As I said, this is a massive force as far as that amoeba is concerned. In fact, what this will do is it will rip the amoeba apart, which is what a centrifuge is designed to do. And it will separate different densities, different parts, different components of the amoeba at different levels on that slanted test tube. That's what a centrifuge does. It can separate cells out into their little chunks. This is a huge force, relatively speaking. Just saying. I like example 2. I like example 2. Example 2 is a nice question. A car is approaching a circular turn that has a radius of 60 meters. If the coefficient of friction between the car and the pavement is 0.45, what's the maximum speed that the car can safely travel through the turn? Calvin, what's this question asking me to find? Speed. Velocity or speed? Speed. So I'm not going to be thinking D equals VIT and all that. Okay. And we're going in a circle. Okay. Is there a mu? Probably a job for a? Probably. The real question is, what's the best free body diagram to draw? Don't write this next bit down, just watch. A lot of students think, oh, I'm going to do a top view. And so they represent the car with a dot. What are the forces acting on this car? Get the obvious one. Which would be into the page. How would I draw that? Normal force out of the page. How would I draw that? So top view is not your best view. What your best view for a car going around a corner free body diagram is a front view. So I'd like you all to pick your pencils up, and what I'd like you to do is right about here, do kind of a little vertical line and then a horizontal line like that. That vertical line is the center of the circle, sort of like the center of the merry-go-round pole that we had Braden sitting on earlier in our thought experiment back when. And I even do that to show that that's the circle that we're going through. I'm going to draw a car. I'm going to do a very stylized car because I can't draw, but I want it to be clear. So here's how I draw my car. I do 2 wheels as rectangles. I put a rectangular front grille with 2 headlights and a little top. That to me looks like it's coming towards me. That's enough that I can figure out what's going on. If you want to, you can also just represent the car with a dot. But just to let you know, this is what I'm kind of imagining. And now, Calvin, what are the forces acting on this car? Get the obvious one. Straight down. And I can see it. Is the car sinking into the ground like quicksand? Is it flying you like Superman? So? Yep. What else? What path is this car tracing out? So where must there be an unbalanced force pointing? Has to be. Has to be. What force is that? Now, I'm not going to call it FC because FC does not show up on my free body diagram. What force pushes cars around corner? You all know this. Of course it's friction. That's why you can't drive on ice. There's my free body diagram for going around a corner. Vertically, forces are balanced. Horizontally, I'm going in a circle. Who's winning? Toward the... So who's winning? Friction. Who's losing? It's a trick question. I get this. Friction is what's pushing me in a circle. Calvin, friction is what times what? Which version of AC am I going to use here? Well, I got to be fussy, the one with speed. Why? Because they asked me for speed. So if they ask for or mention or give me speed, use the v squared over r. If they ask for or mention, the other thing I could have asked if it was a full circle is how long to go one lap. That would be finding the period. But here, Calvin, I don't know the normal force. Oh, but look. So I'm going to get mu mg equals mv squared over r. What? Are you saying that cars and trucks and buses can all drive on the same roads? We don't have to build separate road structures for every different mass? Well, that's a good thing. What are you trying to get by itself, Calvin? How? Hello, darkness, my old friend. Hello, Gur, my old friend. The square root of Gur. Yes, other stuff, but I probably set this up right because I'm going to get V equals the square root of mu Gur. The fact that there's a square root of Gur probably set this up correctly. Yay. Mu 0.45. G 9.8. R 60. What do you get? You get 16.3 times by 3.6, about 58 kilometers per hour. If you've ever approached a corner and you see them, they've put a speed limit sign up, changing the speed limit, this is how they would calculate it. Now, in real life, you would assume it was raining and you would reduce the coefficient of friction by a lot. You always anticipate for a worst case scenario. And also in real life, most corners are banked, not flat. They're at an angle. Did I say angle? I usually look at the banked corner in my last lesson in this unit, but I'm just not going to get to it. But for what it's worth, if I was being accurate as a road engineer, I would say, sure, you can calculate the safe speed with a banked corner. It's fairly easy to do and kind of cool. Anyways, for us, for a flat corner, 16.3 meters per second. An empty swing on an amusement park ride has a mass of 10 kilograms. If the swing has a kinetic energy of 460 joules, what's the centripetal force on the swing? How many of you have ever been on this ride before? The musical swings? Okay, right? Playland has one. Often carnivals, if they come, they have one. Sorry? There's also the one that rises up and swings around. That one is the not. It's not the Beast. It's called the something else. I can't remember.
It's the purple one.
Atmosphere. Yeah, that one's a good one too. Yeah, Playland has one on the ground as well. Yep. That one's considered, I think, a fairly tame ride. Like, okay. Okay. Well, AJ, what's this want me to find? Okay. FC equals MAC. The real question is, which version of A am I going to use? Good question. What did this question give me? What's the equation for kinetic energy? V. You know what? I'm already thinking I'm probably going to use the one with the V in it because kinetic energy has a V in it. So on my next line, I'm going to go FC equals mv squared over r, and I'm going to pause. Do I know m? Yep. Do I know r? From the picture, 7. Right? By the way, although the rope is at an angle, can you see the circle that we're tracing out is a horizontal circle? So we can handle it. I don't know v, but let's go now take the kinetic energy. So you told me that kinetic energy equals a half mv squared. So 460 equals mv squared over 2. Cool. Let's get the v by itself. AJ, how would I get the v by itself? How will I move the m over? And then, wait. You know what? I'm not going to get the v by itself. I'm going to get the v squared by itself because there's a v squared over here. I could square root it, but then over here I'd square it again right away. So this is going to be a little weird. Instead of getting the v by itself, I'm just going to get the v squared by itself and plug that whole thing in. So I think here v squared equals 2 times 460 divided by m. I can replace the v squared with a 2, a 460, and an over m. And if I do that, I'll get m over r 2 times 460 over m. Oh, ha! How many of you have been on a musical, on the musical swings, or been on these? Okay. Next time you're on it, notice very carefully, an empty swing will not swing out further. It will not swing in shallower. It will swing out as the same angle, at the same angle as a full swing with a person in it. Not quite. A person will be a tiny bit in because you have air resistance that the empty swing doesn't have. But the mass cancels, which, yeah, kind of cool. In fact, I'm going to get this. FC is 2 times 460 divided by 7. Which is what? So 100, I'll call it 131 newtons. Next page. I like example 4. I like example 4. Example 4 is a nice question. Here is a better road engineering question. It says this: a car can travel without slipping at a maximum speed of 22 meters per second in a circular path corner of radius 72 meters on a dry horizontal surface. But when it rains, the coefficient of friction is reduced to 1/2 of its original value. What's the maximum safe speed of the car under this wet condition? This is the road speed you would post. What's this question want me to find? Speed, and not 22. In fact, I'm going to guess my answer is going to be less than 22 because it's raining. With me so far? Raining. You know what? Here's what I think I'm going to do. I'm going to divide my page in half. And I'm going to divide it into dry and raining. I'm going to start to solve this question for when it's raining, and I have a feeling probably partway through I'll end up, oh, I don't know this, and I'll have to go walk to where it's dry and figure out the this. Does that make sense? So car going around a corner, my free body diagram is going to look something like this. Here's the corner that we're going around. Here's the car coming out of the page towards me. Kieran, what are the forces acting on the car? Get the obvious one. What else? What else? Which way? Inwards. In fact, for a car going around a corner, and maybe I might even have remembered this and I might even have started there, I would have said, you know what? Friction is what's pushing me in a circle. Mu mg equals mv squared over r. Sarah, can small cars and bikes and buses all go on the same roads? And people can walk on those roads too? Cool. And we again end up with V equals the square root of mu ger. Do I know r? Do I know the radius? Yep. Do I know g? 9.8. Do I know the coefficient of friction? Okay, so you know what I'm going to do? I'm going to, for the coefficient of friction on the right, I'm going to put a subscript of r for raining. I'm going to go find mu dry, and then I'll just divide it by 2. I see where we're going with this. So I think when we're going around the corner dry, it's going to be the same free body diagram, so it's going to be friction is what's pushing me in a circle. It's going to be mu mg equals mv squared over r. But under the mu, I'm going to put a d for dry. Again, the m cancels. What do I want to find on the left? I want to find, hey, what's mu? I don't know what's mu with you. So how would I get the mu by itself? The coefficient of friction. Yep. When it's dry, if you can go at that speed, what was the dry speed? Sorry? 22? 9.8. What was R? 72? This is your minimum coefficient of friction when it's dry. I get 0.68594. That's mu dry. How can I figure out mu when it's raining? Take this number and, yep, divide by 2. So I'll make a little note on the right-hand side. Mu raining equals 0.343. Cool. .343. I'm going to use my answer button. Times 9.8 times 72. Square root. times 9.8 times 72, square root of 242. And I get 15.6 meters per second. I should point out, if you took the corner at this speed, you would not feel safe. You would feel through the steering wheel that your car was right on the edge of skidding. And so you would not do this. You would still knock off a healthy safety margin if you were a road engineer and designing this. So same with when we found the safe speed on this one here. If you did it at 16.3 meters per second, you would be, oh, I feel like my car's about to skid off. So slow down. Little technical comment on turning. So the reason that friction is inwards has to do with how wheels work. When you turn, the car wants to keep going in a straight line at a steady speed, Newton's first. So let's suppose you're making a left turn. You point the wheels to the left. They actually push on the road in that direction. Forces come in. The road, friction, pushes in that direction, which is towards the center. So it's a complicated little dance that we do when we go around a corner. But the short version is, yeah, friction is what's pushing you around the corner. So in horizontal circles, the vertical forces are typically balanced. The net force is inwards, and it's mv squared over r, or m4 pi squared r over t squared. And then the speeding up, slowing down forces are balanced or zero. Unlike the vertical where we had on the roller coasters, you sped up on the way down and you slowed up down on the way to the top. Okay? Put your pencils down, look up.
This is the Royal Air Force Training Centrifuge at Farnborough, and the team here are going to push me as far as they are allowed to push a civilian.
The centrifuge has been here since 1955. The device was originally installed for research purposes, although these days it's used for training as much as it is for research. What it does is recreate the forces that you feel in an aircraft. For our routine pilot training, the first time pilots go on the centrifuge, we expect them to get up to 5G without a G suit and then up to 7G with an anti-G suit.
Now, I'm not taking a significant risk here. I'm healthy, I've pulled a few Gs before, and the human body can take this. And the reason we know that is because in the 1950s, the US Air Force used rocket sleds to push volunteers to incredible speeds.
In fact, I think I showed you those videos last year. We analyzed them, right? John Stapp and his staff.
But that rocket-powered acceleration wasn't the dangerous or even the really high G part of the test. See, high G acceleration takes a lot of incredibly expensive rockets or big old centrifuge like this. But high G deceleration, all you need for that is a wall. Or for something less destructive, like rocket sleds, you use scoops dropped down into a water trough. US Air Flight Surgeon John Stapp, aboard the rocket sled Sonic Wind #1, holds the record for the highest sustained G-force anyone has ever voluntarily endured, 25 G for 1.1 seconds, with a brief peak over 46 G.
In fact, I think we calculated that, as a matter of fact. We got that 46 G, right?
He was badly injured, but he survived and he recovered. He lived to the age of 89. The human body is an incredible thing, particularly because we didn't evolve for this.
G tolerance is something that's innate in all of us. Some of us have high G tolerance, some of us have low G tolerance. Over the years, people's G tolerance doesn't really adapt. Any shortfall in G tolerance has really got to be made up by physical exertion in the G-straining manoeuvre.
What the centrifuge doesn't have is much jerk. And jerk is a technical term. In the same way that acceleration is the rate of change of speed, jerk is the rate of change of acceleration.
For my calculus students, the derivative of acceleration is jerk. This centrifuge accelerates smoothly and decelerates smoothly, so the change in acceleration is very small. Okay?
And because it takes time to spin up and spin down, oh, here we go! Even though the acceleration is high, the jerk here is relatively low, about 1 G per second. Jerk is the difference between a rocket to space, which might take a couple of minutes to reach peak acceleration, and a fighter jet, where manoeuvres might change the G-force acting on you in a fraction of a second. And it can go further than that. You can measure the rate of change of jerk. which is called snap or jouts. The two derivatives after that are called crackle and pop, but they're not all that useful in the real world.
As we increase the G that Tom is exposed to, the blood's going to be pushed down into his feet, and he's going to have to work really hard to push that blood back up to feed oxygen to his brain to keep him conscious. And in real life, we would be expecting that person to be flying an aircraft whilst doing that.
I'm getting a little bit of grey out. I can't quite see.
So about 3.5, 3.6 G.
We teach the anti-G straining maneuver, which composes of two separate parts. First of all, muscle tensing, so both the buttocks and the legs, squeezing the blood vessels to try and get the blood back up into the chest and the head.
Making your face go red on purpose. You will learn to do this when you're 5 or 6 years old.
But also the second part is a breathing maneuver, which increases the strain in the chest, directly increasing the blood pressure to the great vessels in the chest and keeping him conscious.
So you remember the video we watched of the tourist, you could hear the pilot doing the breathing exercises, but the tourist did not do very well. And Tom's only got about another 10 seconds or so.
When you lose blood pressure to your head,
so he's doing the breathing exercise, he's trying.
And we term that G-induced loss of consciousness or G-lock.
So G-lock is something that pilots talk about, G-induced loss of consciousness. When you're flying a plane, blacking out is a bad thing. So he's trying. Nope.
Blimey! I lost everything there. Wow!
G-lock in itself is not dangerous, but the real point is when you G-lock, you're flying an aircraft. So if you're not able to fly that aircraft, I'm sure you can appreciate that that is a real problem.
Because of John Stapp and all the volunteers like him that rode the rocket sleds, there is a lot of research into acceleration on the human body. How many Gs can be withstood for minutes at a time? How many Gs can be withstood for brief moments? And how many can be withstood with training that I clearly don't have? Rocket scientists and roller coaster designers use that data. But there's not much research into jerk, because how do you test it without also testing acceleration?
So one thing we haven't done much research on is the human response to jerk. Because you think about it, what you need to build is some kind of a device that doesn't have a big acceleration, as they're changing acceleration. You're speeding up, you're slowing down, you're speeding up, you're slowing down, and that's kind of tough to do without also having acceleration. So which one are you measuring when you're looking at your human volunteers? The effects of acceleration or the effects of the jerk? Okay. So that's one. And circular water slide. What are the forces acting on him? Get the obvious one. Okay, what else? Normal force up. What path is he tracing out? So where must there be an unbalanced force pointing? What force is that? He would call that tension from his arms. Now, if you ask him, he would say, no, I'm getting pushed outwards, because he's not used to having to pull inwards to stay in one place. Okay? But he is applying the tension through the rope from his arms. He's applying the force.
Don't go in there.
Also, did you notice once he let go, he did not fly straight out from the center. He went, fancy word, tangent to the radius. Your speed is at right angles to the radius. Okay? There you go. What's your homework? You can try number 1. You can try number 2. You can try number 3. Number 4 is the car going around a corner, but with no numbers. In other words, just prove that that's the equation you end up with. We kind of have already. 5 is good. 6 is good. 7 is good. Clearly you can skip number 8. Number 9 is good. Number 9, I gave you the speed at 55 kilometers per hour. Please make sure you convert it to meters per second first. 10 is good. 11 is good. 13 is good. I skipped 12.